We have a very interesting topic to talk about today. Right now I'm sitting on a page that doesn't have anything to do with the topic that we're talking about today, but it is involving this telescope's data. So I'm going to talk about this telescope a little bit, and then we're going to talk about the actual thing today. To kind of put the little hook right at the beginning, today we are going to be talking about the supposed defeat of MOND. For those who don't know, MOND stands for Modified Newtonian Dynamics, and it has been going head-to-head with proponents of lambda CDM, or cold dark matter, basically asking what is keeping all of these galaxy clusters and all of the individual galaxies together, even though there's not enough luminous matter there to hold them together based on what we know about general relativity. There's something missing. The proponents of dark matter say, well, it's a bunch of mass, a bunch of matter that we cannot see electromagnetically, so it doesn't shine, it doesn't reflect light, it doesn't emit light, but it is still there, acts gravitationally, and oddly enough, supposedly doesn't actually, since it has no electromagnetic reactions, doesn't have collision between itself or other forms of matter, since there wouldn't be any way for those electrons to push off each other if they don't interact electromagnetically. So that's dark matter. The other proponents are people saying, well, maybe it's not extra matter, but it's actually just a difference in how gravity acts at larger scales. So the thought being that as you get further and further away from a massive body, Newtonian dynamics and general relativity both agree that you should fall off at 1 over r squared, so if you go twice as far away, it gets 4 times weaker, 3 times as far away, 9 times weaker, etc., etc., etc. However, MOND proposes that at a certain cutoff, you stop following that law and instead start following a different law of gravity, which they call modified Newtonian dynamics. Now, to be completely honest with you, I'm not super familiar with the actual mathematics behind MOND. From what I understand, there's an extra term that they add in addition to Newtonian dynamics that only takes place at a certain distance scale, and from that distance scale outwards, MOND will apply in addition to the normal gravity. More or less, both of these ideas can lead to the same result. The idea being that we have faster rotational curves on the edges of galaxies than the actual luminous matter would suggest inside of them. The question for a while now, I think this has really been going on for the past 20, 30 years, has been, is it dark matter? Is it MOND? And if it's either of them, why is it MOND and how does MOND work? Or what is the actual dark matter that is there? That's the open question. The papers that I'm going to discuss today say two very different things, but one of them has a pretty damn good reason for us to say that MOND might be on its deathbed, which is someone who has always been a proponent of dark matter for the longest time. Hooray. I don't know if that's like a happy thing, but it does exclude MOND as a theory pretty significantly, and we'll talk about it. Before we talk about the actual papers and what they tell us, let's talk about the data that they used and the instrument they used to collect it. So the data that these two studies used, it was the same data set, they just handled things a little differently, which gave you two different results. Both of these data sets come from Gaia. I talked about Gaia a little bit back when I talked about Euclid, because both Gaia, Euclid, and JWST are all floating out at the L2 point, or the second Lagrange point, beyond the orbit of the Earth, in a position that effectively cancels out all the gravitational pull from the Sun and the Earth, alongside the virtual force of it being pushed out due to rotation. So the centrifugal force that these probes will experience will effectively be equally and oppositely canceled out by the gravity pulling them back towards the center of the system of the Earth's sun system. It's not super important. We're not going to talk about the physics here. The important thing is that Gaia is going to effectively be flying around alongside the Earth for its orbit, and it's going to be up there taking data for, well, as long as it works. But the original proposed mission time was about 5 years. And while it's doing that, it's going to be taking tons and tons of pictures, but unlike Euclid and JWST, instead of focusing on the distant past and the distant galaxies that exist far, far, far out, we're going to be instead looking at individual objects inside the Milky Way. So this telescope is looking a lot closer to home, and it's trying to look at individual things inside of our own galaxy so we can learn about those. Now, it does a lot of stuff. The reason we're talking about it is that it is taking data for things that are very, 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 very dim. There is a system in astronomy called the magnitude system. The magnitude system is an old, outdated thing that we stick with because everybody uses it. That's just how it goes, kind of like the imperial system. It makes no sense. The things that you need to know, as someone who is not an astronomer and is just listening to me talk about astronomy, you need to know two things about the magnitude system. The first thing is that it is a logarithmic system. The other issue with magnitudes is that they're reversed. A high magnitude is a dim star. I don't know why. Well, I do know why. Historically, that's how it's always been. It's just how it works. I'm sorry. If we have a magnitude 10 star and a magnitude 9 star, the magnitude 9 star is brighter in the sky than the magnitude 10 star. It's reversed. To put this into perspective, Polaris, the North Star, for those of you in the Northern Hemisphere, which I think is everybody who normally watches me, Polaris has a magnitude of around 2. It's relatively dim. But Gaia is looking at stars that have magnitude of 20 or lower. So we are looking at incredibly dim things that we would never be able to see with the human eye especially. Really only something as delicate as Gaia that's out in space and doesn't have any of these other pollutant effects like we would have on Earth can actually see these objects. And not only is it going to check these, but what it's also going to be checking is what's called the parallax. Here's something for everyone to do. I know that everyone's probably listening to me in the background right now, but if you are, I want you to actually listen to me for a second and actually participate in something with me. Take your finger, put it about arm's length away from you. Close one eye, and then open the other one while closing the first one. Basically, flicker your eyes back and forth. What happens to the finger as you do that? It's a little hard to see at an arm's length, but you'll notice if you pick an object in the distance and you close one eye and then switch to the other one, it'll move a little bit in the opposite direction. So if I'm starting with my right eye and then I open my left eye and close my right eye, the object, my finger, moves to the left a little bit in my view compared to background objects. Closer to your face, you get that same effect but much, much bigger. That's parallax. Effectively, we can use that position in the sky as we move around the sun, and we look at the same object compared to distant background galaxies and stars. We can say, oh, it moved this much, which means it has about this angular separation, so it's about this far away. Now we know its actual distance. And we can use this for a lot of things in the galaxy, but once we start to get outside of the galaxy, this is a useless measure. But this is the first step in the distance ladder, for those of you who remember me talking about the distance ladder. And if we can find a star's parallax, and we can see how bright it is in the sky compared to other things that we know, now we know how actually bright it is. This thing can find parallax, and what it can also do, since it's able to measure those types of differences, it can actually measure the velocity of the star in the plane of the sky, which is called proper motion, and we can figure out how fast is it actually moving in its own relative frame. So if we pick a star in the distance and we say, okay, its parallax is this, we know how far away it is. From that, we can then figure out if its proper motion is this, okay, it's actually moving this fast, because we know how far away it is, we know how fast it looks like it's moving, which means that now we can figure out how fast it's actually moving thanks to trigonometry. This was then used to effectively find a selection of what are called wide binaries. Here's a binary star. This is a contact binary, but what we're effectively looking at is a system like this where we have two stars that are orbiting a common center, but we're talking about wide binaries. We're talking about things that are way further away from each other than this. This is not what we're looking at. We are looking at stars where their distances apart as they orbit are very, very, very large compared to most systems that are binaries. So we're looking at those wide binaries, and the reason that we're looking at those wide binaries is because theoretically, at the distances that these wide binaries are placed, we should start to see effects of MOND if it is true. Furthermore, we shouldn't see the effects of dark matter. Since the dark matter halo is so spread out across the galaxy, if it is in fact there, we should not expect to see effects from that dark matter acting on these individual wide binary systems, but rather the entire galaxy as a whole. If MOND is correct, though, then we should see those MOND-like effects on the scale of these wide binaries. It feels custom designed for this question. Can we see if MOND is true? It does not tell us if dark matter is true, but it does tell us if MOND is true, and we can actually see its effects. So let's look at these papers. This first paper is one in a series of papers that this gentleman and other people have written on regarding MOND. This paper goes as far as to say the data that they see from Gaia has a 5 sigma significance in favor of MOND. 1 sigma is effectively your standard deviation from your average. You're effectively saying if I go on either side of my average by 1 sigma, there is, I believe it's a 60-something% chance that your actual value will lie within that value. It's a measurement of confidence. 5 sigma is a lot. That's really good confidence. So what did they actually do? Well, like I said, they were looking at wide binary stars, and they were trying to see if the effect of MOND was obvious on those individual pairs of stars. One big problem about this is that they needed to figure out the inclination of these systems, because it's one thing for us to say, okay, the binary is going like this, so we can see the effect of the velocity mainly on the wavelength that it's emitting as it gets closer and further away from us, each of the objects. But if we tilt that and now we're looking at it like this, well, we don't get those same effects from the Doppler effect. Instead, we just have them moving in space, so we can't really measure them. And they can be anywhere in between on that inclination scale as well as this way. which doesn't affect our data as much, but it is important to include this degree of freedom in order for the math to work out. So that was their first step, was figuring out what these inclinations were actually doing, and then extracting the actual velocity information as these things orbited around their common center from that inclination. That was the first step. I'm not going to go into how that's done, not really important to the story here. Long story short though, they did a lot of data, a lot of reduction, and what they eventually got, this is the plot here that we care about, was this. So let's talk about what we're actually looking at here. First, I'm going to look at these axes. On the bottom, we have log base 10 of S in AU. This S here is referencing how far away these two objects are. It's log base 10, so you take 10 to whatever value is here. That is how many AU, or distances from the sun to the earth, each of the binaries are from their partner. For example, over here at 3, these are 1,000 AU apart. These individual stars that are orbiting each other are 1,000 AU apart. On the other scale, we have the same log scale, but in this case, it's the velocity. These are the velocities of their motion. These are linear velocities, so if we were to just pop the other one out of existence, how fast would the other one be moving throughout space? Of those objects, again, on a log scale. If we're at 0 here, then this would be 1 kilometer per second. If we're at -1 here, this would be 1/10 of a kilometer per second. These are very fast. All of these data points in the back, these red points, are individual points that they achieved from the Gaia data. These are individual binaries, and they are again plotting their velocity on the y-axis and their separation on the x-axis. Now, all of these points are way too much to actually just glean anything from. We need to do some sort of statistical reduction in order to actually get anything meaningful out of this. So what they did was this. They took each of these sets of data, you can see these dotted lines, these gray dotted lines, which are not data, and they took everything inside of those bins and they effectively took an average. They said, we're going to take all of the data inside of these bins, average their velocities, and then plop that point down in the center of the bin. They did that for 1, 2, 3, 4, 5, 6 bins, and then they plotted those. Effectively, they made a scatter plot. It's a lot more complicated than that, mind you. They didn't just pick these bins willy-nilly. It is worth noting that that is effectively what they did. What they found was that this black dashed line here that represents Newtonian gravity and this small dotted line that represents MOND effects, the data in red starts to deviate as you get to higher and higher separation distances. So starting over here at about 3.1, so 10 to the 3.1 AU, it's still lining up alongside all of the data prior to it with what we would expect from Newtonian dynamics. But it then starts to deviate as you get higher and higher, suggesting that as you go further out, your rotational velocities maintain a higher speed than they should, thus being in favor of MOND. So why did I start this off by talking about MOND is dead? It seems like I'm showing the exact opposite here. Well, there was another paper that was published, well, pre-printed, really recently, like 2 days ago, which is when I found this, that says the exact opposite. This paper suggests that Newtonian dynamics is preferred at 19 sigma. It's really high confidence, wild amounts of confidence here. This paper says we found MOND. This paper says MOND can't be possible. So which one is it? Let's take a look at what this paper did differently, and also take a quick note that this paper is 45, the last 3 are references, 45 pages long. I did not read this whole paper, I'll be completely blunt with you. I'll take you through some of the important stuff though. The main thing they did differently was where this paper took a lot of the data and just kind of threw it in and said, we're just going to use it. The Bannock paper, the one that says MOND is not true, did a whole bunch of selection requirements. So here's a set of them, and then after that set they did this set of requirements, and then after that set they introduced another set of requirements, and if a wide binary met all of those requirements, it was deemed of high enough quality to be included in the study. A lot of people who haven't done science think that this type of restriction of data sets is indicative of some sort of cherry picking. It's not. This happens all the time, especially in astronomy. The data that we get from astronomy is often pretty bad. When I was doing my thesis, some of the data that we were dealing with, the error bars were gigantic, and the results I got, the error bars were gigantic, and that's expected. We're not looking for perfection, we're looking for any amount of data that we can then take and reduce down to useful information. So this is taking a whole bunch of stuff, mainly stuff for which the actual velocity that we're looking for isn't too uncertain, and taking just that data and doing a similar analysis to what the Che paper did, with an important distinction. The Che paper took all of these results and binned them and effectively averaged, which is not really how you want to do something like this. The reason you don't really want to do that is because that gives you no information on whether or not you're actually looking at the thing you say you are. To just bin these is to say, here is a physical characteristic I am looking at. However, the Bannock paper takes it a step further, and it uses something called Bayesian statistics. Bayesian statistics say, given some information, what are the odds that my results align with this hypothesis? In this case, what they did is they said, given MOND or given dark matter, what are the odds that these wide binaries fit in one of those models? That was what they did. And they did it in a really interesting way. So what they did was they introduced this new parameter, this thing they called alpha grav. What alpha grav is it is a parameter that they basically made up, and they said, all right, we're going to change all of the parameters for gravitation to have one set where we're talking about dark matter and one set where we're talking about MOND. And we're going to make this new parameter that's a function of those other parameters, and if it's 0, it lines up with dark matter. If it's 1, it lines up with MOND. And you might question, well, oh, they just made this number up. That's fine. It doesn't matter. It's just a characteristic of all of the other values that they played around with in the simulations and the data analysis. It's basically a summary of all of the other aspects of the study in one number that says, hey, either this is MOND or this is dark matter. If it's 0, it's dark matter. If it's MOND, it's 1. Importantly, this does not exclude something in the middle. This alpha grav term could end up anywhere less than 0, greater than 1, in between 0 and 1, but we just picked those two numbers 0 and 1 as arbitrary points to say 0 represents dark matter, 1 represents MOND. It could be anything in between or on either side. So they ran a bunch of simulations with both of these sets of parameters, both the dark matter and MOND parameters, and they threw all of that against the real data and did a Bayesian statistical analysis to basically say, given what these results from our simulations show, what are the odds that these real results fall into either dark matter or MOND or something else completely? And when they do that, they find this result. When we're plotting alpha grav versus itself, we are looking at the probability distribution of the different values of alpha grav, higher being more likely. And what we see is sort of like a bell curve that peaks pretty close to 0, with not a 1 in sight. This is really good evidence that suggests Newtonian mechanics rather than MOND. I should also make a quick edit. When I say dark matter, I don't mean this is proving dark matter. I mean this is excluding MOND. It's going with Newtonian dynamics. That's important. Sorry about that. This is basically telling us, hey, we have a really high confidence that on average, the results that we see from Gaia line up with results we would expect from a lack of MOND from Newtonian dynamics, which is huge. And not only did they do that, but they also took a look at their actual cuts that they made to see what effects that would have on the actual distribution. So here is the original sample. And I'm not really going to talk about this very much, but this dotted line in here is where we'd expect these data to line up if MOND was true. And these individual data points are, again, basically binned values for the data set. And you can see that they follow this dotted line up and then shoot up as we get to higher separations, and we get what looks like MOND. This was the original version. This paper over here, the Che paper, used these about 26,500 things. When you apply those data cuts that I was talking about before and reduce the number by less than 20%, and just take away the ones that we're not very confident in, this preference for MOND, as it follows this dotted line, completely drops out. Furthermore, they also basically just tried this again a bunch of times, and they said, all right, if we wanted to, how close could we actually get this alpha grav term to match up with MOND? They said that we're going to take all of our simulations and run them again with different parameters that more favor MOND than they should. And how close can we get alpha grav's most likely value to be to 1? The highest they could get in reasonable circumstances was about 0.15. Not even close. Now you might ask, all of this, what does it matter? People who don't like MOND have been talking about MOND in a bad way for decades. Everybody who is a dark matter proponent says that MOND is crazy, says that it doesn't make any sense, blah, 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 yada, yada, yada. Why does it matter what this paper says when we have a MOND expert saying that MOND is probably true at a 5 sigma confidence? What is this guy coming in here saying that they have a 19 sigma confidence that MOND isn't true? Of course they're going to say that. You know, they're not a MOND guy. However, this guy right here, first author, Indranil Banik was the top MOND supporter for the past 10 or so years. He literally wrote the book on MOND. So this 45-page paper with a 19 sigma rebuff of MOND was first authored by the top person in support of MOND. If that's not a bombshell, I don't know what is. So not only do they do all this good science and find out that MOND is basically selected out, but it's written by the guy who was supporting MOND for the past 10 years. This is pretty good evidence that MOND might be on its way out. This is very strong evidence. I should note, Banik here also does not suggest in any way, shape, or form, he even goes as far as to say it in his discussion, that this does not prove lambda CDM. He is still very skeptical on lambda CDM, I can assume. This does not prove lambda CDM, and he is correct. This just disproves our current understanding of MOND. At first, when I read these papers and was looking this stuff up, I'm like, well, yeah, it makes sense that there's going to be one paper saying it does and one paper saying it isn't. They use two different statistical methods, yada, yada, yada. And then I found out that this guy was literally the guy who wrote the book on MOND, and I was kind of floored. So yeah, it looks like MOND might be on its deathbed. It's not like I'm happy to see these guys be wrong. Don't take it that way. But I always kind of didn't really see the evidence for MOND, and having further confirmation on this by the guy who wrote the book on it is very interesting. And I really, really can't wait to see what people make of this paper, because like I said, literally got pre-printed 2 days ago. It was uploaded to the archive literally 2 days ago. We'll see what happens. But this is pretty big stuff. When they say strong constraints, 19 sigma is really strong.